Hello everyone, welcome to this video lecture of basics of Boolean Algebra. So Boolean Algebra was developed in 1854 by George Boole, and it is different from this ordinary algebra, but some theorems are similar to this ordinary algebra. This Boolean algebra is also different from this binary number system. In binary number system 1 plus 1 is 1 0, but in Boolean algebra 1 plus 1 is taken as is equal to 1, means one high is taken as high. So we are starting with some of the laws of Boolean algebra. So the various laws of Boolean algebra are: first one is the commutative law, which states that A plus B is equal to B plus A. And second one is A dot B is equal to B into A. So it means that the inputs can be interchanged in OR gate and in the AND gate. So this is the in the OR gate and in the AND gate. So in both the gates the inputs can be interchanged. This is the first laws in the Boolean algebra, that is the commutative law. And second one is the associative law. Associative law states that, I am writing it as number 3, A plus B plus C is equal to, it can be written as A plus B plus C, and fourth one is A dot B dot C is equal to A dot B dot C. So it means that input of OR and AND gate, this for the OR gate and this is for the AND gate. So this associative law states that the input for the OR gate and AND gate can be grouped in different ways without affecting the output, right? So the inputs can be grouped in different ways without affecting the output. This is defined by this associative laws. And third one is the distributive law. Distributive law states that A plus B dot C is equal to A plus B into A plus C, and sixth one is A dot B plus C is equal to A dot B plus A dot C. So this is a distributive law. It can be written like this. So fourth one comes the OR laws. And these are seventh number, A plus A equal to A, right? A plus 1 equal to 1. A plus 1 is equal to 1. A plus 0 is equal to A, and A plus A complement is equal to 1. So these are the OR laws, and there are AND laws, which states that A dot A equal to A, same. 12th one is A dot 1 is equal to A. 13 is A dot 0 equal to 0. 14th is A dot complement is equal to 0. This means that when we are complementing something with itself and ANDing it, then the result or output will be 0. Similarly, when we are complementing with itself a number, then ANDing it or ORing it, when we are ANDing, when we are ORing it, we are getting the output at C1, and when we are complementing and then ANDing it with itself, we are getting it output at 0, right? So when a number or is ANDed with a 0, we are getting the output at 0. When a number is ANDed with 1, we are getting a number itself. When a number is ANDed with itself, we get the number itself. When a number is odd with its complement, we get the 1. When a number is ANDed or with it with 0, we get the number itself. When the number is or with 1, we get the 1 itself. And when the number is or with itself, we get the number itself. Sixth one law is called as double inversion laws. And it states that A double complement is the A itself, is the number itself, right? Then redundancy laws. Redundancy law states that 16th is A plus AB is equal to A plus A bar B is equal to A plus B. Then A bar B plus AB is equal to A bar plus B. And 19th is A bar plus AB bar is equal to A bar plus B bar. You have to cram it. This is for BTech students. BTech students, you just cram it. Then A plus B into A plus C is equal to A plus BC. Right? So these are the redundancy laws. These are some of the laws under the Boolean algebra. Next comes the duality theorem. Duality theorem states that we can derive another Boolean relation by changing. How we can derive another Boolean relation? By changing each or sign to and sign and changing each and sign to or sign. And next, what we have to do? Complementing any 0 or 1 appearing in the expression, right? And the example is, let us say, one means what you have to do for the duality theorem. You change the or sign to and sign, change the and sign to or sign, 0 to 1 and 1 to 0. For example, you are given a Boolean expression like this. So you have to derive another Boolean expression from this. So it's, or you can say the new expression or its dual form of this expression is A, here it is and, change it to plus sign, B, C, or to and, equal to and to or, and to or, So this is the dual form of each other, right? So this is the duality theorem. Clear? Next is, let us solve this question. Prove a plus b into a plus c is equal to a plus bc. Now these type of, for these type of questions we have to use those laws in picture. So by using those Boolean algebra laws, we have to reduce or we have to prove these right hand side equal to left hand side. So opening this, so what we will get, a into a is a into a is a plus ac. Simply like we do in ordinary algebra, you open the brackets, plus ab plus bc, right? This is the right hand side. Now a into a is a. See the Boolean law. A into a is a plus ac plus ab plus bc equal to a plus bc. Now taking these two, a is common. This is 1 plus c plus ab plus bc is equal to a plus bc. Right? Now 1 plus c is equal to, this is, and oring something with 1. So this is equal to 1. So a dot 1 plus ab plus bc equal to a plus bc. So this is also according to the Boolean law, 1 plus c equal to 1. Similarly, a into 1 equal to a plus ab plus bc equal to a plus bc. So by applying the laws, you can reduce this expression. Sorry. So this is a common. This is 1 plus b plus bc equal to a plus bc. So now 1 plus b is equal to 1. So this is a into 1 plus bc equal to a plus bc. So this is a plus bc equal to a plus bc. So this is proved. So using these Boolean laws, you can prove and also you can reduce any Boolean expression. We will see in the next slide. So why you have to reduce any Boolean expression? So the question is, simplify the expression and draw this logic circuit. Y is equal to b into a bar plus c bar plus a bar into b bar. So this is an expression, we have to first simplify it, or the question may be reduce the expression. Why we have to reduce it? Because we want to simplify the circuit. We want to reduce the number of gates which will be used to realize it in the hardware in the circuit. Otherwise you see what we have to use, how many number of gates we have to use, how many number of gates we have to be that is to be utilized without simplifying or without reducing this expression. Count the number of gates. This is, here it is or and gate, one complement, one or not gate, second not gate, one and gate, one or gate, another or gate, another not gate. So two, here you can see two and gates, two sorry, 4 NOT gates and 2 OR gates. This much you require, right? So this is without simplification. So total number of gates 8 you require. So now let us simplify. So for simplification, let us simplify it. Open the brackets. It is a bar b plus this is b c bar plus a bar b bar, right? So this is equal to, taking these two terms, a bar common, b plus b bar inside the bracket plus bc bar. Now from the laws, b plus b bar is equal to 1. So this is equal to a bar dot 1 plus b c bar. So this is equal to a bar plus b c bar. This is y. So now the reduced expression is y is equal to a bar plus b c bar. Now see how many gates you require. This is one NOT gate, second NOT gate, two NOT gates, two NOT gates, and how many AND gates? One and sorry, one OR gate and one AND gate. This much gates you require. Total number of gates 4. So the reduction in the number of gate is now reduced by 50%. So simplification of Boolean expression is very much important, and so that the circuitry you are making is, the size of the circuitry should reduced and the size of the circuitry should be very small. Miniaturized size is requirement of the day, right? Let us take one more example to simplify of simplification. Simplify y is equal to a plus b into a bar plus c to b plus c. Now we have to simplify this. First of all, let us see how many number of gates required before simplification. How many number of NOT gates? It is only one. OR gates and AND gates. How many AND gates are required? 1, 2 and 3. NOT gates 1, 2 and 3. Total number of 7 gates are required, right? Now let us simplify. For simplify, open the brackets, a into a bar. Let us write it as a into a bar plus ac plus then ab bar, or ba, let us write it as like this, plus bc into b plus c, right? Now a into a bar is 0 according to the law. So this is ac plus ab bar, sorry, a bar b plus bc into b plus c, right? So we have removed this first term because it is now equal to 0. Now again coming to the opening of the bracket. So now this is a b c with first term and this first term a b c plus ac into ac is ac plus a bar b, the second term with this a bar b plus a bar b c plus, this is this similar to the ordinary algebra. This is how we open the brackets in the ordinary algebra, plus bc plus bc, right? Because it is b c b, it is b into b is b and c into c is c. So I'm not repeating, writing it as b into c into c. It is b into c, c into c is equal to c, and b into b is b according to the Boolean law. So this is ABC plus AC plus A bar B plus A bar BC plus this is BC and this is also BC. So BC plus BC is also BC, right? Now this is ABC and this is A, or we can take this is AC common. AC common from these two. AC common, this is B plus 1 plus A bar B common from these two. This is 1 plus C plus BC. So B plus 1 is 1. So this is AC plus A bar B plus BC. So this is AC plus A bar B plus BC. Now again reducing it, it is equal to AC plus A bar B. How you can reduce it? Now this is an important step, you have to see it. This is BC into, now 1 can be written as A plus A bar. I can write 1 is equal to A plus A bar, right? So I have written 1 equal to this. So this is equal to AC. Just for the simplification purpose, I have written 1 here as like this. So this is ABC plus A bar BC, right? And this is equal to A, taking these two, AC common, this is 1 plus B, and taking these two and writing it as A bar B common, it is 1 plus C, right? Now 1 plus B is equal to 1, this is AC plus A bar B. So now Y is equal to AC plus A bar B. So this is the simplified. So now you can see not gate 1 and gate 2 and OR gate 1. So now the number of gates are 4. Number of gates is now reduced from 7 to 4. Clear? Regarding the realization of the circuit, as we have seen the reduction of the Boolean expression. Now to realize a Boolean expression, now let us say the realization of this expression y is equal to a plus b, a bar plus c into b plus c we have done. We have reduced this circuit to y equal to ac plus a bar b. Now how to realize this circuit? Realization of a Boolean expression means that we have to make a circuit of this expression in the form of gates, logic gates. So how we have to make a circuit? Here we can see there are 3 variables given, a, b and c. A, b and c, right? So first term is AC, means a AND gate is used between A input and C input. And we know the symbol of AND gate. This is the symbol of AND gate. This is the first term. In the second term, A bar B. A bar B means this is the complement over the A input, and then a AND gate is applied between A bar and B. So for the between the A bar, you put a NOT gate for the A bar. So this is A bar and B. We are taking B from here and putting a AND gate here, and then output of these two gates is taken and a OR gate is applied to the output to get the final output Y. As you can see, the final output is or is plus sign is there, which is denoting the OR gate. So we get the final output. So this is the realization. This Y is now, this is, here we are getting A, C, here we are getting A bar, C, and now Y is equal to AC plus A bar B. So this is the realization of any logic circuit. So first we have to reduce the Boolean expression. Reduce means we have to reduce the number of logic gates so that less number of gates are used while making the circuit, and then realize in the form of a hardware circuit. Clear? Next, moving on to the Boolean expressions representation. So when we write the Boolean expression, there are three forms representation of Boolean expression. In the three forms we can write the Boolean expression. First one is called as sum of products. Sum of product form. Second is product of sum form. And the third one is canonical form. Canonical form or standard form. Right? Sum of product, in short it is called as SOP, and product of form is in short it is POS, and in SOP it is called as sum of product, means the AND terms are odd. Here OR terms are ANDed together, right? Example is A, B, C plus A bar B. Here this is ANDing of the variable is there, and then ultimately these are odd. Here A plus B plus C, this is ORing of the terms, ORing of the variables, and then ultimately these are ANDed with A bar plus B. So this is ORing of the terms, and then ultimately these are ANDed. So this is the POS form, product of sum. This is sum of product. And in SOP these terms are called as minterms. And in POS these terms are called as maxterms. Right? And these minterms are denoted by a small m, and these are denoted by capital M. Right? And in minterms, 0 is taken as a complement and 1 is taken as a normal, as a high, or 0 is taken as a low and 1 is taken as a high. But in max it is opposite to minterms. So here 0 is taken as high and 1 is taken as low. Now, what is the canonical form? It can be a SOP or POS form, but contains all the variables. Example is A, B, C plus A bar, B, C bar. This is a canonical form, means this is an expression y is equal to A, B, C plus A bar, B, C bar. Now, how is it different from SOP? It can be SOP, but in the canonical form. Y is equal to AB plus AC bar. That is also a SOP, sum of product. But that is not a canonical form because all the three variables are not present in all the terms. Here ABC, all the three variables are present in all the terms. Here C is missing, here B is missing. So if any variable is missing in any term, then that form is not standard form. Clear? Now, a Boolean expression can also be represented in terms of minterms and maxterms. As we have seen that the representation of Boolean expression like this ABC plus ABC bar plus ABCD bar, right? This is a common representation of Boolean. But in terms of minterms, we can also like this. This is 0, 1, 2, 3, 4, like this, or it can be written as pi m 1 5 6 7. So this is also a form of writing Boolean expression. Now this shows that the Boolean expression is given in the form of small m, shows that is SOP form. Sum of product capital M shows that is POS. Now when we are writing it as small m, it is sum of product. This is summation sign. Summation sign also shows that it is sum of products, and pi sign shows product. So that's why it is product of sum, right? So let me also tell you about the minterms in terms of what these 0 and 1, 2, 3, 4 signifies. Now these signifies that what terms are present in the Boolean expression. Now this 7 also represents the how many variables are present in the Boolean expression. As we know, 2 raised to power n generally we use in the digital, right? So if n is equal to 3, this means 2 raised to power 3 is equal to 8. So if n is my number of variables, so the maximum terms I can have is equal to 8, and the terms will be from 0 to 7. So here 7 represents that my number of variables will be equal to 3. So if I am having equal to 4, this means that I am going for 3 variables, because if I am having n equal to 2, then 2 raised to power 2 equal to 4. So my number of terms will be equal to 4, but the number of variables will be 0 to 3. So maximum number will be 3. But now I am having number 4 also. So for that I require number of digit 3. That in digital it is required. So note down this, that if I am having 4 variables, digital counting, I suppose from 0 0 0, as these are 4 variables A B C D, and counting from 0 0 0 up to 1 1 1 1. So this is 0 0 0 1, this is 0 0 1 0, this is 0 0 1 1, and so on up to all ones. So in min terms, these are max terms. So how you will write it as? This is M0, M1, M2, M3. This is nothing but binary counting. Similarly, this will be capital M0 up to capital M15, right? Now, in terms of this binary, these variable terms, how you will write as? M0 means this will be A bar, B bar, C bar and D bar. And M1 is A bar, B bar, C bar and D, because I told you earlier that in sum of product 0 will be taken as 0, or complement we will take for 0, and or low, and 1 will be taken as 1, high. So this is the normal nomenclature we will follow for the min terms or the sum of products, right? So for 0 0 1 0 it will be A bar, B bar, C and D bar, and so on. For A15 it will be A all ones, A, B, C, D. So this is the normal thing we are following for the min terms. But for the max terms it will be opposite to minterms. So for the max term, what will happen? You will take 0 as normal, and for 1 you will take the complement. So for M0, what you will write? And this will be product of sum. So you will write it as A plus B plus C plus D. And for 0, 0, 0, 1, so a will 0 will now here will not be complemented, here 1 will be complemented. In 1, in min terms 0 will be complemented, in max terms 1 will be complemented. So it is a plus b plus c bar plus d and so on. So 1 will be complemented. So it is A bar plus B bar plus C bar plus D bar, like this. Clear? Now converting from min term to max term or max term to min term, the steps will be as follows. Right? So write down these 4 steps. First, what you have to do, change are ors to ands and all ands to ors. So this is the first step you have to do. And second, complement each variable. From whatever form you have to go, from either max to min or min to max. These are the 4 steps you have to follow. Complement each variable. Right? Means you have to complement each and every variable, means you have to add bars over each variable. Third is complement the entire expression. Means you have to add a long bar over the entire expression. Then last one is eliminate all groups of double bars. Eliminate all groups of double bars, because when you are complementing double, the number itself is coming, so you have to eliminate the double bars, right? So these are the 4 steps you have to follow for the conversion from max term to min term or min vice versa. So let us take an example. So one example is, so this is an expression f is equal to, or y is equal to x bar plus y bar plus z bar, x plus y plus z bar. So these are the max terms are given to you, and what form it is? This is product of sum, right? And this is the whole bar is given to you. So this expression, Boolean expression, is given to you. You have to convert this expression to min term. Convert it to min term. Now what is the solution? First step is convert all ors to and all ands to or. So first step is f is equal to x bar into y bar into z bar, right? Plus x dot y dot z bar, right? This is the first step we have done. All or to and to or. Second step, complement each variable. This is first step. Second step, complement each variable only, right? So this is x double bar, y double bar, means earlier it was there, plus x bar, y bar, z bar, and this is the original bar in the problem is there. Third is complement the entire expression. X double bar, y double bar, z double bar, then plus x bar, y bar, z bar. Sorry, this has to be double bar, right? Double bar, and this is double bar here now, right? And then fourth one is, now the last stage is elimination of the double bar. This double bar is to be eliminated, this double bar eliminated, this has to be eliminated. So this is x y z plus x bar y bar z, and this whole is eliminated. So now the expression is xyz plus x bar y bar and z. So this is the answer. So now this has reduced from max terms to min terms, or from POS form to SOP form. Clear? So in the next class, we will do the simplification of Boolean algebra or Boolean functions by the 4 methods are there. So that we will be covering in the next class, right? Thank you.